Hey, ladies and gentlemen. So, past me forgot to make the final video of this. So, you get present, Mr. Lacconi, to do this final bit of notes for homeostasis and transport and all this fun stuff. All right, so we are now talking about active transport. And lucky for you, this is a really short section. All right, most of the stuff you need to know about for this, we've already talked about in the other two sets of notes. So, we are good to go. Now, we just got to talk about what makes things happen actively. What I mean by that is we require energy to make things happen. Before, things were just happening, right? That's passive transport, when things just happen. You know, you put a tea bag into a cup of hot water and the chemicals in that tea just spread. Nothing makes that happen. The tea is not making itself spread out, right? Active transport is the opposite. All right. Imagine trying to stuff that tea back into the tea leaves, right? That's one thing very difficult to do because the tea is trying to go outward. You're fighting what's going to happen, right? And that's going to require energy. So active transport is when things are going to go the wrong way on purpose. Your body wants it to go the wrong way on purpose. So your body is going to put energy into it. And by energy, I mean ATP. Active transport requires ATP, right? Adenosine triphosphate is the word. Here's where the word comes from, guys. This is a molecule, and it consists of something called adenine. Please remember that for the DNA chapter. That comes back to haunt you. Adenine, ribose, which is a type of sugar, and three molecules called phosphates. Adenine and the ribose together is called adenosine. There's that word. And then triphosphate. What's tri mean again? Tri. Tri means three, like tricycle or triceratops. Triphosphate, three phosphates. So adenosine triphosphate. That's where you're going to get your energy from. And when you use that energy, you do so by ripping this phosphate off, and you are left with adenosine diphosphate. Di means two phosphates. Oh, and you know that extra phosphate you ripped off. They're both floating around inside your body, and all that energy came out, and you get to use that energy. So think of triphosphate as a charged battery, diphosphate as a dead battery. So then, this, guys, yeah, I made a model of adenosine triphosphate. Stop covering this stuff here, right? So adenine and a ribose, that's adenosine, and then we got three phosphates, right? Your body is going to rip this phosphate off, and all the energy is going to come out. I was going to be fancy and have like the light come out here, this flashlight, but look at it, it's broken. Best laid plans, whatever. So all that energy is coming out, and you can serve off the energy, but now you used it. It's a dead battery, and it's just floating around inside your body, and this phosphate is also floating around inside your body. And last chapter, yes, last chapter, we talked about cellular respiration. We talked about breaking open the sugar and getting all that energy out. Well, your body's going to take this, and it's going to take this and try to catch that energy. It's going to go, where? There. And now the energy's stuck in there again. All right? One sugar was 38 of these, right? 38 of these caught energy. Now you got triphosphates. That is what you are using for energy. So when it's time to do something, crack, energy comes out. And now you get to do something. And then you just recharge this later. Recharged. And we're going to talk about two basic ways that this works. Right? Two very simple ways that we are going to use our energy to make molecules move the wrong way on purpose. The first one is called pumps. Now, I used to have an animation right here, and that is now gone for some reason. So don't worry, I've got you covered. So pumps, which look like this, right? This is a protein. This is the cell membrane. The protein is in the cell membrane. And see, I told you I got you covered with the animation. All right. And all those molecules are floating around. Normally, the molecules on out here want to get in, but it's closed, door shut. But all these molecules down here Now see this empty space, passive transport says, oh, spread out. It's being tricked because it's shut. Once they go in, here comes your ATP. Let me make this a bit bigger here. See that ATP down here at the bottom? Can I move this out of your way? Yes, I can. Excellent. And boom, it attaches. We break the phosphate off, and you see a little flash there? Boom, energy. That energy comes out, which forces this protein to change shape, and your body now used its energy to force this stuff out. And now that it's open, same thing happens. Some other chemical, potassium, by the way. This was, oops, I rewound. That's sodium. Na is sodium. And it gets kicked out. And then K is potassium. Potassium comes in, and when the energy of this phosphate runs out, the protein changes back, and the potassium is now inside the cell. This is why this is called a sodium-potassium pump. Sodium because it kicks sodium out, potassium because it forced potassium in, and it's a pump because we are using our own energy to make it work, just like a bike pump. Just like a bike pump where you force air in, even though air wants to leave the tire, use a pump to force it in. Sodium wants to go this way, and we use our energy to make it go that way. That is your sodium-potassium pump. So there is a lot of sodium outside the cell. Instead of going in like it wants to, the pump uses energy to force more sodium out. And then the exact opposite with the potassium. Potassium wants to get out. We use the energy to drag it in. I said there were two ways we were going to talk about this. The pumps was one, and the other one is called, actually it's two subcategories, endocytosis and exocytosis. Endocytosis, there's your cell, all right? This black here is the cell membrane, and oh, these organelles are in the way. Let me get rid of those. Thank you very much. And this is some kind of molecule that you want in, but look, oh no, oh no, oh no, oh no, we don't have a pump for that. There's nothing, we can't drag this sucker in. So we have a backup solution, right? This membrane can wrap itself around it and pop off. And now we got a little bubble. And this bubble can drag it wherever it needs to go in the cell. If that's sugar, it can go to the mitochondria. We call this endocytosis. Endo means to enter. Endo means enter, or to having to do with the inside. And then cytosis, it's going into the cytoplasm of the cell. This literally translates to entering the cell, or entering the cytoplasm. And this bubble, by the way, is called a vesicle. Endocytosis, creating a vesicle to enter the cell. That's how you get nutrients in if you don't have a pump. And then, of course, sometimes we want to kick it out. We call that exocytosis. It's the exact opposite, but it's the same process in the opposite direction. Creating vesicles to exit the cell. So now that we use this, there's nothing left but leftover waste, right? Mitochondria got a hold of it, and now it's just trash left over. So we want to kick that out. That vesicle, the bubble right here, is going to reattach to the membrane and open up and kick the trash out. Exocytosis, to exit the cytoplasm. So we got this nice little guy, and the membrane is going to wrap around it. See how that happened? Wraps around. Oh, I got a whole bunch of stuff here. And that's a bacteria the cell is trying to eat. Engulfs it, and look at that. The membrane that's wrapping around it attaches to itself and pops off right there. And now this membrane, this vesicle, can carry this bacteria anywhere it wants. And that's usually going to be a digestive organelle. The lysosome will break that down. And we got some liquid chemicals, same thing. Drag it in, and boom, now they're on the inside. Here's how it happens. On the membrane, we got these little receptors, or catchers, going to grab the molecules we want, drag it in, and force the membrane to attach on either end, and now we have a bubble. we call a vesicle. And we can do the same thing. We can exit. We can make that vesicle reattach and kick all the stuff out. Exocytosis. So, endocytosis, dragging stuff in. Oh, too fast. And exocytosis, kicking stuff out. All right, ladies and gentlemen, that is it for active transport. So go back, make sure you understand all the vocab, make sure you understand all of the structures of everything, the passive transport, the active transport, because now that I'm actually fully planned, you're getting a Laconia that's been planning now. Ha ha ha. Your vocab quiz actually would have been today. Be prepared for that if you didn't take it yet. You will be having more notes on homeostasis, positive feedbacks, and a test coming up Wednesday the 18th. So be prepared for that. Wednesday the 18th is your test on all of this stuff. All right? All right, one more set of notes, and I will see you then. Have a great day, guys.